All right, cool. So today I'm going to talk to you all about some WB commands, surface and metric resample, and also surface sphere project unproject. And these commands all rely on the use of barycentric interpolation. So I'm going to start this tutorial by giving you guys a little bit of background on that. And then I'm going to move on to the commands themselves, trying to give you guys a general intuition, and then also going through some common examples. And it might not be super useful right now to just look at these examples, but hopefully this is something that you can revisit if you're trying to use these commands. So let's start from the absolute basics. Interpolation, what is it? Well, say that I have some colored shape. It could be a triangle, like in this image here. Let me see if you can see my mouse. Yes. And I know the color at points A, B, and C. Now say that I wanted to know the color at point X. How would I find that out? Well, the answer is using interpolation. So you'll all have encountered this before, but maybe a bit more of a familiar example is the following. Say that I've got this curve here, but I don't actually know what its equation f of x is. Well, I just know the values at some specific points, and similar to before, I want to know the value of my function at some location x, where it hasn't been explicitly defined. What to do? Well, I can approximate or interpolate my function in a few different ways. The simplest here would be a linear interpolation. So essentially, I'm approximating my curve using this linear fit. And as you can see, it's not a very good fit, but nevertheless, we can now obtain a possible value of our function at point x here. And this will intuitively be a weighted average of our values at x1 and x2, and where whichever point is closest will have the most influence. Now, there are many other interpolation methods out there. Some common options include nearest neighbor, where your value at point x won't be a weighted average, but rather just the exact same value as that of the closest neighboring point, or cubic interpolation, where instead of having a linear fit, we can fit a third-degree polynomial. And of course, these can all be extended to higher dimensions as well. Now, when we're talking about functions and when we're looking at these 2D cases, it's quite easy to visualize these sort of height maps, right? Well, these are actually very similar to images, where you again have a set of xy coordinates, and instead of corresponding heights, where's my mouse gone? Here. Instead of corresponding heights, you have intensity values or colors. And here we can imagine that if we wanted to find the intensity at some point xy in between these 4 points or pixels, this intensity would be based on the respective distances to the other points, such that, just as in our linear interpolation case, the closest point has the biggest influence, and then it goes down the further away you get. So if we return to our very first example, we can imagine a very similar scenario. So our color at x is just going to be a linear combination of our colors at the 3 vertices, where alpha, beta, and gamma are weights that assign how much influence each vertex will have on the color of x. And the formal method for calculating these weights is just called barycentric interpolation. And it's basically just linear interpolation using 3 points instead of 2, or if you prefer, bilinear interpolation using 3 points instead of 4. So there are a couple of different ways that you can obtain these weights, but they all calculate pretty much the same. And since this isn't a maths class, I'm just going to stick to the one that I find the most intuitive. So for each vertex here, you can construct a triangle that lies opposite it using our point x and the 2 other vertices. And you can see that the further away point x lies from our vertex, the smaller this triangle is going to be. And so the most straightforward way of calculating our weights, alpha, beta, and gamma, is just by taking the ratio of the area of this opposite triangle to our total triangle area. So alpha is just going to be the area of this triangle A here divided by our total area. Beta is going to be the area of triangle B divided by the total area. And gamma is going to be the area of triangle C divided by the total area. So you can see that if point X was to lie on the vertex A here, then this triangle would encompass the whole triangle. And so alpha would be 1 and beta and gamma would all be 0, as we would expect. So as these are all ratios as well, it's clear that they should sum to 1. And a few spoilers, I guess, when I'm talking about resampling later, specifically in the context of surfaces, all that we're doing here really is estimating these barycentric weights or barycentric coordinates of different locations and then using these to estimate data values at those points. So now that I've given you guys this little bit of background, we can move on to the actual contents of today's tutorial, our workbench commands. Cool. I'm going to start with the resampling commands. And these can be used in two similar but slightly different ways. So either we can use resampling to just change the resolution of a surface or metric file, or we can use it to apply a registration and change its coordinate space. So if we think about resampling just as changing the resolution of an image, we're just changing the number of pixels, or on the surfaces that we work with, the number of vertices, while still maintaining the overall representation of the image. So for example, if you upsample or increase the resolution of your image, you're increasing the number of pixels or vertices using some form of interpolation. And as we saw earlier, on the surfaces that we work with, barycentric is the way to go, since they're just composed of a bunch of small triangles. Now, upsampling can result in smoother, more detailed images, but it can also introduce artifacts, especially if the original image was of low resolution. If you downsample or reduce the resolution of an image, on the other hand, you're instead removing some of the pixels or vertices. And this can result in a coarser, less detailed image, but it can also reduce the amount of data needed to represent the image. Now, in certain instances, this understanding of resampling is very appropriate. So say, for example, that we have a 32K sulk map, and we want it in ICO4 instead, say, in order to speed up the runtime of some statistical analyses. Maybe you're running FSLPOM. Then the command that we would use is metric resample. So when we're using this command, we start by always typing out wb command metric resample, and then we need an input metric. So this is just the metric file that we're resampling. A current sphere, which is a spherical surface that has the mesh that the metric is currently on. A new sphere, which is a spherical surface that is in register with a current sphere. And a method. So this method is add-up bary area, that's what's recommended for metric resample. And this is a sort of adaptive barycentric interpolation method where we can input other data to sort of guide and do an area correction. So basically our barycentric interpolation is slightly weighted by this other data. And usually this would be a mid-thickness surface. And then the metric out is just what we want to call our output metric file. And note here that WB command specifies that the new sphere has to be in register with a current. Since we are just downsampling a mesh and nothing's being deformed, just scale down, it's implied that our spheres are in register. This isn't always the case though, so I'll get to that in a bit. But basically, whenever you're just changing the resolution, you don't have to worry too much about this. Cool. So let's look at an actual example. You can obviously look at this in more detail later, but I'll just sort of talk you through it. If we wanted to change the resolution from 32K to ICO4, then we would start with a 32K metric file as our metric in. Our current sphere would then be the 32K template sphere. Our new sphere would be the ICO4 sphere. And for our output is whatever we want to call it. This is just going to be the ICO4 metric file. And our current area would be a 32K mid-thickness surface, and the new area would be the ICO4 mid-thickness surface. And these are what we're using to do the vertex area correction based on. Cool. So anyways, consider now a situation where we didn't just want to look at a subject sulk map in a different resolution, but where we wanted to compare sulcal depth across many subjects. Now we'd need to ensure that our subjects were aligned such that the same spatial location corresponded to the same anatomical location, and basically that they all existed in the same coordinate space. So if we wanted to do this, we would start by running MSM and registering our subjects to a template, which usually would be sort of blurry population average. And as you know, when we run MSM, we choose one or more cortical metrics to drive our alignment. And for the sake of this example, let's just say we choose sulk. Now, what our registration is doing is it's moving the vertices around on our input subject's native sphere to make sure that there's maximum overlap between our subject sulk map and the template sulk map. So to reiterate, you can see here that these vertices get moved around and end up over here in order to maximize the overlap between our input and template sulk maps. So here's a little GIF of an ICO2 sphere without any metric files on it. So you can see a little bit more clearly how vertices might get moved around. You can see that. Yeah, as a result of a registration. Note, this isn't the same registration, it's just here for visualization purposes. And so really we're not actually deforming the metric file here. We're only deforming this underlying surface, right? But note that we're not actually, even though we're just changing this surface, this sphere here, we're not trying to create two spheres that have similar vertex organization. We still only care about the overlap of our feature maps or our metric files. So anyways, you might run your registration and then visualize the metric file on the output sphere and think, great, I'm good to go, everything's aligned. However, that is not the case. So, come on, it's not, there you go. So as I said earlier, we want to ensure that the same location and coordinate space corresponds to the same anatomical location across our subjects, right? Well, a metric file is just an ordered one-dimensional array of data values where each value corresponds to a specific vertex. So in order to actually achieve this goal, we'd need to ensure two things. First, that all subjects have the same number of vertices, and second, that all subjects are in vertex correspondence with each other, or in other words, that the ith vertex always corresponds to the same anatomical region or landmark. So we don't want to end up in a situation where, say, these four vertices here on the motor strip are actually situated in like the occipital lobe of another subject, right? So to apply the results of our registration and ensure that all of our subjects actually end up aligned and in the same coordinate space, we resample. And really, the only thing that's happening here is that we're estimating the barycentric weights using the vertex locations of our deformed MSM warp and applying these to the new vertex locations on our template sphere, such that we end up with the shape of our sulk map, as seen when deformed by the MSM warp, but with a mesh topology of the template sphere. So just to clarify here, the goal is to preserve the shape here of our deformed sulk map, but to just sort of swap out the underlying mesh for this regular 32K template so that all of our subjects are in vertex correspondence and they can all be viewed on the same mesh. So to actually put this in practice, this time around, our metric resample command would look something like the following. Our metric in would be the native metric, just as before. Our current sphere would now be a native to 40-week. Okay, so this is for a DHCP example. If we're looking at the HCP, this could just be our MSM warp. But for the DHCP, this will be a native to 40-week template warp. I'll touch more on that later. The new sphere is going to be the template sphere. Method, again, adaptive barrier area. And then the metric out is just going to be our deformed metric in template space. Cool. And you will note now, sorry, 1 second. Yeah, and so you'll note how here we're using a warp, right? And not just a mesh anymore. And so since we're interpolating this warp and we're applying the deformations from MSM, we need to take a lot more care that our current and our new spheres have been properly registered, right? So that this output aligns with the template, because otherwise we're going to end up applying the wrong deformations to the wrong locations. So we need to be really careful here when we're changing the coordinate space that we've done our registrations correctly. Cool. So to summarize so far, we can use metric resample in two main ways, either to just change the resolution of our metric file. This is super straightforward. We're just changing the number of vertices, or to apply a registration and change the space of our metric file in a way that establishes vertex coordinates correspondence between the subjects, and this can change both the vertices and or their organization. Cool. So say now that we've successfully registered one of our subjects to 32K template and we've resampled all of this subject's metric files, so sulk, thickness, curvature, etc., from native space to template space. Now, in order to properly visualize these metrics and maybe perform some analyses, we also have to ensure that our subject's surface files or anatomies get resampled as well. If you don't do this, you will either not be able to visualize your feature maps or metric files on anatomical surfaces at all, due to them having a different number of vertices, or if you have different spaces but the same resolution, you'll end up with something like what you see here, where the features don't align with the underlying anatomy. So on the left here, we have a resampled curvature metric file in MSM all space on an MSM sulk surface, and on the right here, we have the same MSM all space on an MSM all curvature. Sorry, I'm getting confused with all these names. We have the same MSM all curvature file, but it's on a surface that has been appropriately resampled to MSM all space. And so as you can see, on the left-hand side here, it's a bit of a jumbled mess, but on the right-hand side, the gyra and sulci are very nicely aligned with the intensities that we see in our curvature map. Cool, so the procedure here is very similar to metric resample, but I'm going to go through an example just for completeness. Now, instead of metric resample, we obviously use surface resample, and we have an input surface instead. This is just our native surface. Similar to before, our current sphere is just going to be this native to 40-week template warp for the DHCP, or just the MSM output sphere for adult data. We have our new sphere being the template sphere, and our method here is just barycentric, so we don't use this area correction anymore. And the output surface is just going to be your deformed surface in template space. And of course, if you just want to change the resolution of your anatomies and not necessarily resample them to a different coordinate space, then you can use surface resample for this as well. However, if you wanted to resample the spherical surface, so say your MSM output sphere, to a different space or a different resolution, then you should instead use our next command, surface sphere project unproject. So, as I've said previously, a surface registration starts with an input sphere and it moves the vertices around on the sphere until it matches the template data. And what this means is that the registration deformation is actually represented as the difference between two separate files, the starting and the registered sphere. But oftentimes the starting sphere is just a native sphere, right? And so it's unlikely to have vertex correspondence to any other spheres. And for this reason, it can be very inconvenient to manipulate or compare these deformations across subjects. So if we wanted to apply the deformations onto a new sphere of our choice and essentially resample this spherical surface, surface sphere project unproject would be the way to go. So say here, see if I can start these GIFs, that we've got our, this is our native surface, and then this would be our MSM warp. Let me see. There you go. So you can see how the native surface, this native sphere is deformed slightly. And imagine that we wanted to view these deformations on an ICO 5 sphere instead, so that we can compare it to other subjects. And we wanted something like this. It's a little bit hard to see, but essentially, we sort of remove all these underlying structures and just isolate the deformation itself. Then our command would look something like the following. So start as usual by typing wv command surface sphere project unproject. Our input sphere here is just going to be a sphere that has the desired output mesh, so it's going to be an ICO 5 sphere. The sphere project 2 is a sphere that aligns with sphere in, and this is all a bit unintuitive, and the naming of this command is just, I think it's a bit of a mess, and I know that other people have been very confused with it as well. But this is going to be our standard native sphere. So I guess you can think that they're aligned in the sense that they're both undeformed. And then you have the sphere unproject from, which is just the standard native sphere here that has been deformed to the desired output space. So it's going to be our MSM output sphere, or the warp, which is just the deformed native sphere that you saw here. So this native sphere is going to be our sphere project 2, and then has it shifted already? Did I miss it? Well, when it shifts, that's going to be the sphere unproject from. And then what you finally end up then with is this MSM deformation on an ICO 5. And you can think of it a little bit as unprojecting the MSM deformation from the native sphere and sort of projecting it onto the ICO 5. Cool, so that's pretty neat, but there are more uses to this command. And I think that, at least in our lab, it seems like the most common one is to combine successive but independent registrations. So, yeah. So a very helpful example is actually specified in the command description. And I know that a lot of people use this as a sort of guide and a sanity check. So I'm going to run through it quickly here. Say that you have a human to chimpanzee registration and a chimpanzee to macaque registration, and we want to combine them to get a human to macaque registration. Well, the way that you would do this is to use the human sphere registered to the chimpanzee as your sphere in, the chimpanzee standard sphere as your project to, and the chimpanzee sphere registered to macaque as your unproject from. And this will then give you the output of a human sphere that is in register with a macaque. Maybe a more relevant example is how in the DHCP we register all subjects to a 40-week neonatal template by first registering each subject to a sort of age-matched template, and then in turn registering to a 1-week older template, and so on and so forth until we get to 40 weeks. So for example, say that we have a 35-week-old subject, we'd first register them to the 35-week template, which would then be registered to a 36-week template, and then register with a 37, 38, 39 to 40. So the final output is then this native to 40-week spherical warp, which is kind of similar to what MSM would output. And you might remember that this is the warp that we used in 2 of our previous examples when we were doing metric and surface resampling, and it was then the current sphere. So here is a slightly simpler example that I got from Mariana. It's just a 36 to 38 week and 38 to 39 week registration combined into a 36 to 39 week registration. And I don't think it's super useful for me to read through this, so you can look at this in your own time if you need to do something similar. And finally, you can also use surface sphere project unproject if you want an inverse registration. So say that you had a human to chimpanzee registration, but you wanted the sphere as if you'd run the registration from chimpanzee to human instead. Well, the way to do this would be to use your chimpanzee standard sphere as the sphere in, the human sphere registered to the chimpanzee as project to, and the standard human sphere as unproject from. And this would then give you the chimpanzee sphere in register with a human as your output. And here again, if you want to look at it later, is an actual example from Mariana, where we take the inverse of a native to template registration in order to get a template to native registration. So hopefully that has given you guys some examples that you can use to get through these commands, and also a little bit of a better intuition on how they work. Cool. I think that's it.
I think that was really good.
I talked a lot faster than I was planning on, so it was a bit shorter than when I timed it at home, but
Just more time for questions, I think.
uh,
No. I was just going to say with the surface resample thingy, like it is important for viewing the metric files on individual subject anatomy, but like an additional case is that if you wanted to create a group average anatomical surface, depending on what registration you had done, in order to do that, you would need to resample all individual anatomical surfaces into whichever space you were interested in, and then you can average them. So like a lot of us will be viewing our metric files on a single template, like very inflated surface. And the way that you do that is you first need to resample all individual very inflated surfaces into that template space so that they can be averaged. But
yeah.
it's the exact
I'll
same.
add that.
Yeah. Because I think a lot of people would like, how does the template very inflated surface get created? And that's how it is created.
Okay,
so that's the only thing I wanted to add or clarify.
Cool. Yeah, that's useful.
I mean, the only point that I had was that, you know, when you talk about oversampling, you can't insert detail that doesn't exist.
Yeah, exactly.
So you can't really add detail.
Well, it will appear as if it's more detailed, won't it? But it will just not be real.
You can't, well, it's not adding detail, it would just be adding information, but like adding samples, but you can't, in terms of what's encoded in the data, you can't create data that just doesn't, you can't create information that doesn't exist. So you can lose information from downsampling, but you can't insert information. I mean, that's where you have things like super resolution and AI and stuff that learn to sort of insert the data from learning that mapping from other data.
Right,
But
I
it could
see.
Cool.
I guess that's also a good thing to clarify a bit more then.
I mean, it's such a small thing. Like, mine and Nick, I didn't really have any other points.
Cool.
I guess another thing in terms of that resolution example is that the resolution of the surface needs to match the resolution of the volume that you're projecting your data onto. So like for structural things like cortical thickness or T1 over T2 maps, they're acquired at a very high resolution, like 0.7, 0.8 millimeters cubed. And so the surface that you would, the most appropriate surface for that would be something that's close to 160,000 vertices, where your vertex spacing is roughly the same as the voxel spacing.
Right. But that's not a requirement, is it? It's just a ideal
No, it's not
situation.
yeah, exactly. That's not a requirement. It's just ideal. And then the reason that I think we use 32K for the adults anyway is that the 2 millimeter spacing for the fMRI is captured by a 32K surface where the average spacing between vertices is around 2 millimeters. So you're trying to sample your surface at the same resolution as your most coarse volume.
Okay, cool.
I guess that's a bit of reasoning as to why you would choose there are biological meanings for the surface sampling, in addition to like, computational requirements like downsampling to an ICO4, for instance.
Yeah. Okay, yeah, that's actually very good. I'll make sure to add that. Simon, do you have a question?
Yeah, just a very simple question. The first example before this metric sample, you showed the option of adaptive barycentric.
Yeah.
But can we just use barycentric?
You can, but they recommend that you use. It says in the command that it's recommended that you use the adaptive one whenever you're doing metric. But it's fine to not do it, I think.
Yeah.
I mean, I don't think you're not committing a crime.
Okay, so it's fine to use barycentric. It's just I'm losing, I guess, some information.
Yeah, I
I'm
think.
not weighting correctly.
Yeah, I think it's more accurate. But I know that it also can result in some smoothing. I don't know if you want, but that's why you don't use it for the surfaces.
And another question I had, but it's maybe I'm not that used to those comments, and I mean using those comments, but from the example you showed from matrix to template on metric, you showed metric resample and then you showed surface resample. I don't understand how the metric resample command does not need the outputs from the surface resample as surface in. Like, how can you resample the metric from your native template without having the surface resample to the template, the native surface resample to the template? That makes sense.
Well, you have. I'm not sure.
Maybe I'm not.
So you have. Let me go back to the slide. Okay. Wait, was it?
Before this one.
Was it here?
So this, yeah. So here you metric in. Okay, so your current sphere is the native.
So you have the template sphere, and your surface is going to be based off of this mesh anyways, right? Like your template surface. So because you have this warp that looks sort of like this, it shows you how it's going to be deformed. And then you have the template sphere itself, which is just it gives you the number of vertices and like how they're organized.
If you show the comment.
I mean, the template is a regularly sampled, it's a regularly sampled sphere. Get weird effects through changes in resolution.
Do you mean that you're surprised that we don't need to use a template surface here? Or
yes, actually, yes.
Well, it's because we have the template sphere.
Yes, okay.
Cool.
The thing is it gets quite confusing, but like that is the template surface. Because once you've resampled to the sphere, then everything is in vertex correspondence.
Yeah, I think he just means why we wouldn't have like an anatomical template surface. But all of the information that would be in that would be captured by this template sphere anyways.
You're never in a MSM warp. I think this is where we all keep getting stuck. There is no actual default, like warping of the shape or anatomy at any stage. It's that the points are moved around on spheres, and that sphere learns an implicit correspondence between two surface domains. And so once you know the correspondence on the surface, on the sphere, then you know what the correspondence is on the anatomical surface. So that's what anatomical MSM uses, right? You're never actually deforming the anatomy. It never moves anywhere. And the points get moved around on the sphere, and from that you then learn an implicit mapping between the anatomies, because you know, if you know what location on the sphere a point has deformed to, then you know what point it's deformed to on the reference anatomy. And this is the bit that Saga has got stuck with for a long time.
I had so many crises.
That's interesting.
And it's also us trying to explain to Nashira and not being very good at explaining to her.
And so maybe I need to do another video, but it's all nothing ever this is why we need a surface to volume. If anything was actually physically getting deformed, we wouldn't need a surface to volume registration, but nothing ever gets moved. Nothing ever moves. The only thing that ever moves are points around a sphere. The anatomies never get moved. So one thing that we were talking about, which maybe I didn't capture whether was in here, was the differences in the resampling. So the FS average space in the HCP and the DHCP, when you look at those surfaces, they haven't moved anywhere. They are the exact original native surfaces. So the actual shape is still in native volume space, but the topology of the mesh has been resampled so that the vertices correspond conceptually across individuals. So vertex 1 corresponds to the same anatomical structure across all individuals, but they're not aligned in space. And that is really quite difficult to wrap your head around. You've actually just mapped the reference topology, so the topology of the graph, which vertices belong to which faces, that matches the reference target mesh. But actually, the anatomy itself hasn't gone anywhere. It stays exactly in the same space, and those meshes are still aligned with the individual subject's native volumetric brain anatomy, which means that then it's useful, because if you wanted to do like a resampling of your functional imaging data from your functional volume into MSML template space, you can just do it. All you need is your fMRI to structural registration, and you've got it in structural space. And from there, you can directly go into surface template space just by resampling. And I've lost everyone.
No, Simon said.
No,
yeah.
no, I'm lost. You understood everything. You understood everything.
So maybe we need some more of these sorts of examples, because it is really, like the number of times I draw this diagram with the little brain anatomy and the triangles, it's very difficult to get your head around. So FS average space is things have never been, the anatomy, the surfaces, they never get changed, deformed. They stay where they are. They just get resampled. And that allows you to do an interpolation or mapping of image data into a surface template space. But we never actually deform the templates themselves, which is why it's so difficult to go from surface template space to volume template space, because there is no averaged those surface templates that you look at. They are generated by averaging surface coordinates after they've been affinely aligned, essentially. So that's why they look so smooth. They're not. If you were to generate an average surface from like a really strongly aligned volumetric image data set, they've been generated by mmorph or something, you'd have a lot more detail in that average surface than what you get with these surface templates. And that's because you haven't actually changed the shape of the surfaces. You haven't deformed them non-linearly. They stay where they are, and then you just average coordinates after they've been affine aligned, and you lose all of the structural detail. Which is why we need a surface and volumetric registration.
Yeah. It might be worth adding a slide to sort of explain that in a bit more detail then.
I think maybe, but it's a tricky one. So, I mean, maybe you need something to explain what FS average space is. It's not like you could basically just swap between one FS average anatomy from one subject to another, and you'll see that they're not aligned.
Yeah.
They're not spatially aligned. So there's that.
Cool.
Thank you, Saga.
Are there any other questions? Sorry, you were going to say something, Emma.
It's just super difficult to wrap your head around. You just keep having to go back to it again and again and again.
Yeah.
I thought this was really good. This is a really good presentation. I'd even say I would just take this recording and maybe cut off some of the end of the discussion and put it up. But maybe at some point we need to kind of get more into some of the trickier aspects as well.
Yeah, it might be worth doing a sort of part 2 then, where we get into like nitty-gritty details. So like we can, I guess maybe it's good to have one which is just general intuition and then one which is sort of specifics. And then based on how much you need, like, because not everyone's going to need to know all the specifics, but if it's relevant to some people, then it should, I guess it's good if there's another video for that.
Perhaps. I mean, you wouldn't say that everybody needs to get into. You don't necessarily have to go further and be implementing them at the level that you are, but kind of really understanding what FS average space is and how it differs from what you're trying to do, I think is quite important.
I think that'd be useful for me as well, because I don't know. I don't think I know enough about it. And I guess that would be a good way for me to actually make sure that I learn it properly.